There is a dangerous idea that sounds intelligent the moment you hear it. It appears in documentaries, billionaire interviews, science conferences, and futuristic animations showing glowing cities beneath glass domes on the surface of Mars. The idea is simple. Mars looks hostile today, but hostility is just an engineering challenge. Build stronger habitats, create artificial farms, recycle air and water, cover the planet with technology, and eventually humanity becomes a multi-planet species. It sounds ambitious, it sounds inspiring, but hidden underneath that optimism is one of the most misunderstood assumptions in modern science. Because Mars is not simply difficult, Mars may be physically incompatible with long-term human civilization in ways most people have never fully understood. The problem begins with how humans imagine space itself. Most people think of space as emptiness, a silent vacuum with nothing inside it. But that picture is deeply incomplete. Space is not empty. Space is violent. It is filled with streams of subatomic particles crossing the galaxy at speeds so extreme they carry energies beyond anything produced in our most powerful machines on Earth. And these particles are not harmless background noise. They are one of the biggest reasons Mars may never become the second home humanity dreams about. To understand this, stop imagining space as an empty void and start imagining it as an invisible ocean. Not an ocean made of water, but an ocean made of atomic nuclei traveling close to the speed of light. These particles are called galactic cosmic rays. And unlike the radiation most people think about, cosmic rays are not weak electromagnetic waves that can simply be blocked by thick walls. They are physical fragments of atoms accelerated by some of the most violent events in the universe, exploding stars, collapsing systems, and enormous magnetic shockwaves moving across deep space. Now imagine standing behind a giant wall made entirely of fragile glass. On the other side of that wall, someone fires an armor-piercing round at incredible speed. Your first instinct is to trust the wall. You assume the barrier will absorb the impact and protect you from harm. But physics has a cruel surprise waiting for you. The projectile slams into the glass with such force that the wall itself explodes. Thousands of razor-sharp fragments burst outward in every direction. Instead of stopping the threat, the barrier transforms one incoming projectile into a deadly cloud of secondary shrapnel. That is almost exactly what happens when galactic cosmic rays strike the walls of a Mars habitat. This effect is known as spallation, and it changes everything. Cosmic rays are not light. They are atomic nuclei stripped bare of their electrons. Some are simple protons, but many are much heavier elements like iron or silicon, accelerated to more than 99% of the speed of light. When one of these particles collides with a dense metal wall, it does not gently lose energy and stop. The collision is so violent that it shatters the nuclei of the atoms inside the wall itself. The metal becomes part of the attack. The result is a cascade of secondary radiation. Neutrons, protons, nuclear fragments, and other energetic particles burst through the interior of the habitat. The colonists inside are no longer dealing with one incoming particle. They are being flooded by hundreds of secondary particles created by the very walls designed to protect them. And this is where the dream of simple engineering solutions begins to collapse. Most people assume thicker walls solve the radiation problem, but particle physics says otherwise. Add more metal, and you create more material for spallation reactions to occur. More atomic nuclei become targets. More secondary radiation fills the interior. At a certain point, increasing the thickness of the shield actually increases the biological radiation dose rather than reducing it. That means the intuitive solution fails before the colony is even built. Inside the habitat, the damage would be relentless. Every particle passing through human tissue carries enough energy to ionize molecules and break chemical bonds. DNA strands inside cells begin accumulating microscopic injuries hour after hour, day after day. The body can repair some of this damage for a while, but over long periods, the repair systems lose the race. Mutations accumulate, cancer risk rises, bone marrow weakens, immune systems degrade. Neurons suffer genetic damage that slowly affects cognition itself. And this is happening while the colony still exists in perfect working order. But Mars is hostile in another way most people rarely think about. because the real reason Earth remains habitable is not just its atmosphere or its distance from the Sunday. The real reason life survives here begins nearly 2,000 miles beneath your feet. Deep inside Earth, enormous oceans of molten iron rotate continuously around the planet's core. That moving electrically conductive metal generates a massive magnetic field surrounding the planet. This field, called the magnetosphere, acts like an invisible shield extending far into space. Without it, life on Earth would face the same radiation nightmare waiting on Mars. The reason Earth can support forests, oceans, cities, and billions of living organisms is not simply because it sits at the right distance from the Sunday. That explanation is incomplete. Plenty of worlds can exist in a so-called habitable zone and still become lifeless wastelands. What truly separates Earth from places like Mars is something invisible, enormous, and constantly active around us every second of our lives. It is Earth's magnetic field, and without it, the surface of this planet would be exposed to the full violence of space. Most people never think about the magnetosphere because you cannot see it directly, but it may be one of the most important structures protecting life anywhere in the known universe. Deep beneath Earth's crust, nearly 2,000 miles below the surface, liquid iron and nickel churn continuously at temperatures hotter than the surface of the Sunday. Because this molten metal moves while carrying electrical charge, it creates a giant natural dynamo. The result is a magnetic field that stretches tens of thousands of kilometers into space, forming a massive invisible shield around the planet. This shield changes everything. Galactic cosmic rays are charged particles, and charged particles moving through a magnetic field do not travel in straight lines. They bend, they curve, many are redirected entirely away from Earth. Others are pushed toward the poles, where they interact with the atmosphere and create auroras instead of catastrophic biological damage. Every second of every day, the magnetosphere is quietly deflecting an enormous amount of subatomic radiation that would otherwise strike the biosphere directly. In other words, life on Earth survives because the planet itself actively protects it. Mars cannot do that anymore. Billions of years ago, Mars may have looked very different. Geological evidence suggests that ancient Mars once had flowing water, a thicker atmosphere, and its own magnetic field. But Mars is a smaller world than Earth, and that difference changed its fate completely. Smaller planets lose internal heat faster. Over immense spans of time, the Martian interior cooled until the liquid metal inside its core began to solidify. Once the internal motion slowed down, the planetary dynamo shut off. And when the dynamo died, the magnetic field vanished with it. That moment transformed Mars forever. Without a magnetosphere, the solar wind began stripping away the atmosphere particle by particle over millions of years. Cosmic radiation started reaching the surface almost unfiltered. The planet became exposed directly to the energetic environment of space. Today, Mars is not just cold and dry. It is unshielded. The entire surface exists under a constant bombardment of radiation that Earth's magnetic field normally prevents. This is where the conversation about colonizing Mars becomes physically serious rather than inspirational. Because if Mars lacks a natural magnetic shield, humanity would need to create one artificially, and the scale of that challenge is almost impossible to overstate. Some theoretical proposals have suggested placing gigantic superconducting magnetic generators near Mars to deflect incoming particles. Others imagine building enormous magnetic structures at the Mars L1 Lagrange point, a gravitational balance region between Mars and the Sunday. In theory, these systems could create a partial protective field around the planet. But theory and reality are very different things. The energy demands alone would exceed anything humanity currently produces. The infrastructure would require decades of development, massive industrial systems in space, and technologies that remain largely experimental. We are not talking about building a city or a rocket. We are talking about constructing an artificial planetary defense system operating continuously on a scale beyond anything in human history. And until such a system exists, every Mars colony would remain exposed. That brings us back to the habitat problem. If colonists cannot rely on a planetary magnetic field, they must depend entirely on local shielding. But as we already explored, dense walls create spallation reactions that flood habitats with secondary radiation. The structure protecting the colonists becomes a source of additional danger. So what happens to the human body in that environment? The damage would not arrive dramatically. There would be no cinematic moment where radiation suddenly kills everyone overnight. The real danger is slower and far more destructive. Human biology depends on stable molecular information. DNA is essentially a chemical code built from fragile atomic bonds. Ionizing radiation breaks those bonds constantly. Normally, cells repair the damage, but under continuous exposure, the repair systems begin falling behind. Mutations accumulate. Cancer risk rises steadily. Bone marrow loses efficiency. Immune systems weaken because many immune cells are highly sensitive to radiation damage. Neurons inside the brain also begin accumulating genetic errors over time, potentially affecting memory, concentration, and cognitive performance. A Mars colonist might not feel the effects immediately, but after years inside a radiation-heavy environment, the biological cost compounds relentlessly. And biology is only part of the problem. Every machine keeping the habitat alive would also exist under continuous radiation stress. Electronic systems are vulnerable to energetic particles. A single particle strike can flip digital bits inside computer systems, creating what engineers call single-event upsets. Sensors malfunction, circuitry degrades, semiconductor materials accumulate long-term damage. Meanwhile, polymer seals crack as radiation breaks apart molecular chains. Filtration systems weaken. Air recycling systems lose efficiency. Water purification membranes degrade. Every component holding the colony together slowly moves toward disorder. And physics guarantees this process. The second law of thermodynamics states that ordered systems naturally degrade over time unless continuous energy and maintenance are applied. A Mars habitat would be one of the most fragile, high-order systems humans have ever attempted to maintain. And it would exist under constant particle bombardment every hour of every day. The terrifying part is that this creates a feedback loop. The more systems degrade, the more repairs colonists must perform. The more time spent repairing systems, the more radiation exposure accumulates. The more radiation damage the colonists suffer, the harder it becomes for them to maintain the systems keeping them alive. Mars is not simply dangerous because it is far away. Mars may be dangerous because the laws of physics themselves continuously push against the survival of complex life there. The deeper scientists study long-term survival on Mars, the more uncomfortable the conclusions become. Most discussions about colonization focus on launch costs, food production, fuel systems, or habitat construction. But beneath all of those engineering challenges sits a more fundamental problem. A Mars colony is not simply a building placed on another planet. It is a fragile pocket of biological order trying to survive inside an environment that continuously works to destroy order at every level. And the universe never stops applying pressure. A pressurized habitat on Mars would function like a tiny artificial ecosystem cut off from Earth's natural support systems. Every breath, every drop of water, every degree of temperature control, every electronic sensor, and every recycling process would depend on interconnected mechanical systems operating continuously without failure. On Earth, people rarely think about how many invisible systems support daily life, because our planet itself does most of the work automatically. Earth provides atmospheric pressure, magnetic protection, liquid water cycles, breathable oxygen balance, and thermal stability across enormous scales. Mars provides none of those things. Outside the habitat walls, the average surface temperature hovers near minus 60 degrees Celsius. Atmospheric pressure is so low that unprotected liquid water boils away almost instantly. The air is mostly carbon dioxide and far too thin for humans to breathe. Meanwhile, cosmic radiation and solar particles constantly strike the surface with little resistance. So, the colony must manufacture stability artificially. Air pumps circulate breathable gases through sealed chambers. Carbon dioxide scrubbers remove toxic buildup. Electrolysis systems split water into oxygen and hydrogen. Thermal control units prevent freezing. Pressure systems maintain survivable atmospheric conditions. Water purification networks recycle waste. Food production systems operate under carefully controlled light and nutrient cycles. Every one of these systems is an ordered structure fighting against entropy. And entropy always wins eventually. The second law of thermodynamics is not a suggestion. It is one of the most reliable principles in physics. Ordered systems naturally drift toward disorder over time unless constant energy and maintenance prevent it. On Earth, large-scale planetary systems continuously restore balance. On Mars, the colony itself becomes responsible for maintaining every layer of stability manually. Now place that entire artificial ecosystem inside a radiation-rich environment. The consequences multiply rapidly. Ionizing radiation does not only affect biology, it affects machinery at the microscopic level. Semiconductor materials inside computers accumulate damage as energetic particles disrupt electrical pathways. Random bit flips appear in software systems. Sensors slowly lose calibration accuracy. Polymer materials used in seals and insulation weaken as radiation breaks long molecular chains apart. Microscopic fractures begin forming in components designed to hold pressure and regulate airflow. At first, these failures appear manageable. A damaged sensor can be replaced, a corrupted memory module can be repaired, but over years and decades, the maintenance burden compounds continuously. This is where Mars colonization begins to resemble a thermodynamic trap. Every repair operation requires human labor. But the humans performing those repairs are simultaneously absorbing chronic radiation exposure themselves. As the environment damages the habitat, it also damages the colonists responsible for maintaining it. And the damage accumulates slowly enough to become deeply deceptive. The human body is remarkably adaptable in the short term. Astronauts can survive elevated radiation exposure for limited missions, but a permanent colony is a completely different situation. Chronic exposure over years means cells repeatedly suffer ionization damage faster than repair mechanisms can fully correct it. DNA strands break. Mutations accumulate. Some cells stop functioning correctly. Others become cancerous. Meanwhile, radiation-sensitive tissues like bone marrow gradually weaken, reducing the body's ability to generate healthy blood and immune cells. Even the brain becomes vulnerable. Neurons are not easily replaced, and accumulated molecular damage inside neural tissue may slowly affect memory, focus, and decision-making over time. This creates an extremely dangerous cycle for a long-term colony. The more degraded the systems become, the more repairs are needed. The more repairs are needed, the greater the radiation exposure for the population. The more biological damage accumulates, the less capable the colonists become at maintaining the systems, keeping them alive. The colony slowly loses efficiency at both the mechanical and biological level simultaneously, and Mars offers no natural recovery mechanism. On Earth, ecosystems absorb disturbances and restore balance across massive scales. Earth's magnetic field shields the biosphere. The atmosphere absorbs dangerous radiation. Oceans regulate heat. Biological diversity creates resilience. Mars has none of this planetary support structure. A colony there exists as an isolated island of complexity inside an environment fundamentally hostile to complexity itself. This forces us to confront a much deeper question. What if life does not survive on certain worlds, not because intelligence lacks ambition, but because physics imposes strict boundaries on where complex biological systems can remain stable over long periods of time? That possibility changes the entire conversation about becoming a multi-planet species. Human beings often assume that if something is technologically difficult, it will eventually become achievable through persistence and innovation. But physics does not negotiate with optimism. The laws governing particle interactions, radiation exposure, entropy, and planetary magnetism operate regardless of human ambition. And Mars may sit on the wrong side of those laws. This does not mean short-term missions are impossible. Humans will likely walk on Mars. Temporary research stations may eventually exist there. Scientific exploration can absolutely happen. But permanent large-scale civilization is a very different question entirely. Because surviving somewhere for a few months is not the same as creating a self-sustaining biological future across generations. And when scientists examine Mars through that lens, the planet begins to look less like humanity's next home and more like a warning about the extreme rarity of worlds capable of supporting complex life. At a distance, Earth and Mars can look strangely similar. Both are rocky planets orbiting the same star. Both once contained water. Both experience volcanic activity, changing climates, and complex geological histories. That visual similarity has encouraged generations of scientists and futurists to imagine Mars as a dormant version of Earth waiting to be awakened again. But when you examine the deeper physics shaping both worlds, the differences become overwhelming. Earth is not simply lucky. Earth is protected by an extraordinary chain of planetary conditions that work together continuously to preserve life against the violence of the cosmos. And the more scientists understand those conditions, the more fragile and rare they begin to appear. The first major difference is size. Earth is significantly larger than Mars, and that difference affects almost everything. A larger planet retains internal heat longer because it has more mass-trapping energy inside its core. That heat keeps Earth's interior active even billions of years after the planet formed. Deep below the surface, molten iron still circulates through the outer core, maintaining the magnetic dynamo that generates the magnetosphere, protecting the biosphere today. Mars lost that internal energy long ago. Its smaller size allowed heat to escape much faster. Over immense spans of time, the Martian core cooled, internal circulation slowed, and the planetary dynamo shut down. Once that happened, Mars lost the magnetic shield that once protected its atmosphere and surface. Solar radiation and charged particles gradually stripped the atmosphere away, leaving behind the cold, exposed planet we see now. What makes this so important is that the atmosphere and magnetic field are not separate systems. They work together. Without magnetic protection, atmospheric particles become vulnerable to erosion from the solar wind. Over millions of years, the atmosphere thins. As pressure drops, liquid water becomes unstable on the surface. Climate systems collapse. Radiation levels rise. Eventually, the planet crosses a threshold where maintaining complex biology becomes dramatically harder. Mars may be the clearest example of this process inside our solar system, and that raises an uncomfortable possibility for the broader universe. What if habitable planets are not defined primarily by distance from a star, but by long-term magnetic stability? For decades, astronomers searching for Earth-like worlds focused heavily on the habitable zone, the region around a star where temperatures allow liquid water to exist. But temperature alone does not protect life from radiation. A planet can sit in the perfect thermal range and still be sterilized by cosmic particles if it lacks magnetic shielding. This changes how we think about life itself. Complex biology may require much more than water and moderate temperatures. It may depend on deep planetary structures invisible from the outside. A world capable of supporting life for billions of years might need a large molten core, continuous internal heat, stable rotation, long-term tectonic activity, and enough mass to sustain a magnetosphere across geological timescales. That combination may be extremely rare. And if it is rare, then Earth may represent something more unusual than humanity has fully appreciated. This perspective also changes the meaning of colonization. The common assumption is that advanced civilizations can simply adapt technology to hostile worlds indefinitely. But physics keeps presenting the same obstacle again and again. Technology can delay environmental pressure, but it does not erase it. A Mars colony would constantly fight against radiation, entropy, atmospheric instability, mechanical degradation, biological damage, and extreme energy demands all at once. Every layer of survival would require continuous maintenance with no planetary support underneath it. Earth does the opposite. Earth carries us effortlessly. People often underestimate how much invisible work the planet performs every second. The atmosphere absorbs harmful ultraviolet radiation. The magnetosphere deflects charged particles. Oceans stabilize climate. Gravity maintains pressure. Natural ecosystems recycle nutrients and gases automatically. The biosphere repairs itself continuously across massive scales. Human civilization evolved inside this protective cocoon for millions of years. On Mars, every one of those functions must be artificially recreated. And artificial systems are fragile. The more scientists model long-term colonization scenarios, the clearer the thermodynamic reality becomes. A permanent settlement on Mars would not become easier to maintain over time. It would become progressively harder. Equipment ages. Radiation damage accumulates. Human health slowly declines under chronic exposure. Supply chains remain vulnerable. Energy demands never stop. The colony exists in a permanent state of resistance against environmental collapse. This is why many physicists and planetary scientists argue that the biggest barrier to colonizing Mars is not transportation. It is planetary physics itself. Even proposals for underground habitats only partially solve the problem. Yes, burying colonies beneath Martian soil could reduce radiation exposure somewhat. But underground settlements create new complications involving structural stability, thermal regulation, psychological strain, excavation, logistics, and enormous energy requirements for maintaining sealed environments over generations. The deeper humanity looks for solutions, the more the scale of the challenge expands. And perhaps the most profound realization hidden inside all of this is that the universe may not distribute habitable worlds generously. Complex life might emerge only in rare protected regions where planetary physics continuously shields biology from cosmic radiation long enough for evolution to build stable ecosystems. Without that protection, the subatomic environment itself works against biological complexity at every moment. In other words, the universe is not neutral toward life. It actively filters where life can persist. And Mars may be one of the clearest demonstrations of that filter in action.